Greetings. The problem we solve today is on heating plus humidification. It tells us that we have a system that at point 1, temperature T equals 5 degrees C, V equals 50%, P, the ambient pressure, is 90 kilopascals, and air mass flow rate is 0.1 kilograms of air per second. That's mass flow rate for the dry. Now, it goes into this system, and of course, there are two additions. First, first is heat, and then it is water. We are to calculate heat, but we know that water is added at the rate of 0.0022 kilograms per second, and its temperature is 10 degrees C. Now, what comes out on the other side at 3 is equals 30 degrees C. Pressure is, of course, still 90 kilopascal, and we don't know the rest. We are to calculate how much heat is added, and we are to calculate characteristics of the outgoing flow. That means phi, W, specific humidity, and relative humidity. We are to calculate them all. This is a problem that quite often happens in air conditioning systems at winter. Since the outside air is pretty cold, it's fairly humid at this temperature, but as it is, when it heats up to 30 degrees C, then it is dry for that temperature. The humidity usually drops to around 10% or even less. Now, water has to be added to the system so that humidity increases. And this is exactly what happens here between points 1, 2, and 3. And how we solve this problem is interesting because first we solve it between 1 and 3 and we calculate overall data. But then we go into point 2 and see how point 2 can be decided upon and what quality of water can be added after point 2. Now, what I wish to do is to write down the laws of thermodynamics and see how they would talk us. Of course, the laws of thermodynamics could be written in two ways. First, they could be written for air, and then they could be written for water. But for air, nothing happens with mass flow rate, since mass flow rate of air would remain the same from incoming air to outgoing air. But the water flow rate changes, and then we have to write down some mass conservation equation for the water. Now, as for the energy equation, which is the second equation, now the energy equation could be written for them both. In fact, it has to be written for them both, for all that enters and all that exits. For both equations, the left-hand side is 0. There is no work. And therefore, there is only incoming flow and outgoing flow. Velocity and elevation will be ignored because they are not the problem of us at the moment, and They are too small to consider at this stage and for such problems. So let's start with the mass flow rate for water. And since the problem is steady, the left-hand side is 0, and 0 would equal the water vapor that goes in with the air at point 1 plus the water that goes in at after point 2, in fact, and minus all the water that goes out at point 3. So this is point 1, this is point 2, and this is point 3. Now, in air conditioning problems, we usually simplify everything for air mass flow rate. And we know that W equals m dot V over m dot A. This is the vapor mass flow rate, and this is air mass flow rate. And so if we put it in this equation, 0 would equal W1 times m dot A, W1 times m dot A, and here we could write it m dot F 2 divided by m dot A and times m dot A and minus W3 times m dot A. Of course, m dot A cancels out from this equation, and 0 would equal W1 plus m dot F over m dot A and minus W out. And this is what we get from the mass conservation equation. And of course, we can put numbers to it. But before I do that, I would go for the energy equation and try to write down the energy equation as well. So the left-hand side is 0 for energy equation. 0 equals the enthalpy going in at point 1, which is H in at point 1, plus HF, that is in, and that's at point 2, and minus H out at point 3. These are the incoming enthalpies, outgoing enthalpies, and plus Q dot. And of course, there's no work done. If there was a fan in the system, then we would have to calculate the work done. But as it is, the fan is outside this control volume, and so we don't need to do that. Now we can simplify it. 0 equals m dot A. Instead of that, we could write m dot A times the air enthalpy, which is Cp0 Ta1, plus the enthalpy of water, which is W1 HV1. That takes care of the incoming enthalpies, air and water all together, plus, and that would be m dot F times HF, very simple. And the outgoing enthalpies would be very similar, handled as incoming enthalpies. So I could write it as minus m dot A times Cp0 T A3, temperature of air at point 3, plus W3, and the enthalpy of vapor at point 3 and plus, here we could split Q dot to M dot A times Q. We could keep it as it is, or we could split it up like here. We have, of course, M dot A, so we could calculate it all together in one place. But as it is, there are two ways. First, we could divide everything by M dot A if it was to be solved for per unit of air. And this would be M dot F over M dot A, which is the same as here. Or we could solve it all together in one place. So these are our equations. Now, what we need to do is to find numbers, find properties and numbers for every one of them. And what we have in point 1, there are properties that we have. We have everything at point 1. We have temperature, we have relative humidity, and therefore we could calculate specific humidity, which is W1, and fill in everything in this equation, find W out. And once we have W out, we have W in, we have M dot F, and we have temperatures, all the set for calculating heat transfer rate. And that will complete our problem for the whole control volume between 1 and 3. But it's a good job at the air conditioning problems to make a table for all points at different temperatures and know the water vapor, liquid and vapor properties at these temperatures. You see, in this problem, we have 4 dominant conditions which we have to take care of. First is 5 degrees C, 10 degrees C, 30 degrees C. These are the different points that we have. This is the incoming air and water. This is the incoming water that is added to the system. This is the outgoing. And there's one more, which is 90 kilopascals. And what we need from them are both pressures for the air conditioning problem, enthalpies at saturated liquid, and enthalpies at saturated vapor. And once we have written these things, then it helps us a lot to use them in the calculations that we have. I would return to point 1, where the temperature was 5 degrees C and phi was 50%. At 5 degrees C, we know that the saturation pressure is 0.8725. And therefore, what we do is to write down W equals 0.622 PV divided by total pressure minus PV. And also we know that phi equals PV over PG. And therefore we can calculate PV from phi times PG. Now let's insert values into this equation, and W at point 1 would be 0.622 times. Instead of PV, I have PG, and I have phi, so it would be 0.5 times PG, which is 0.8725. That's the value of PG at 5 degrees C, divided by 90 minus, once again, 0.5 times 0.8725, and therefore W1 would be 0.00303 kilograms of vapor divided by kilograms of air. And this is an additional knowledge for point 1. And with this knowledge, then we can use it in mass conservation equation to calculate W at point 3. So we learned that W at point 1 is 0.00303. Now let's insert it in this equation. 0 equals W1, which is 0.00303 plus mass flow rate for ingoing water, which is 0.0022 divided by 0.1. That's the air mass flow rate, and these are the two values that we were given by the problem. And minus W out. And the only unknown in this equation is the specific humidity at point 3, which is the outgoing flow. Now, the conclusion from this is that W out equals 0.02503 kilograms of vapor divided by kilograms of air. This is the outgoing. This is the outgoing specific humidity. And it's a very good job to use this to calculate the relative humidity at point 3. Now we learned that at point 3, W3 equals 0.02503 kilograms of vapor per kilograms of air. Now, the same equation may be used, but this time W is known and P is unknown. So we could calculate P 4.3. And we may write the same equation, and it is 0.02503 equals 0.622 times P, this time at point 3. At point 3, the temperature is 30 degrees C, and therefore P would be 4.2469, 4.2469, and this is divided by 90 because the total pressure remains the same, minus, once again, P3 times 4.2469. And the outcome for P3 from this equation would be 0.82. This means it is 82%, which is perhaps very humid for living. But look, this enters a room where its humidity is far less, and therefore it mixes in that room, and hopefully it will produce a good enough condition for living. Well, at this stage, we have all the knowledge we need to calculate the first law. This is 0 equals m dot a is 0.1 times CT0 for air is 1.045 times the initial temperature at point 1, which is 278, and plus W1, which we calculated it to be 0.00303 times HV1, which we read it from the table at 5 degrees C, it is 2510.1, 2510.1 at 5 degrees C, and plus water mass flow rate, which is 0.0022 times the enthalpy of liquid water going in, which is the saturation enthalpy at the same temperature, and you are told that the temperature is 10 degrees C, so this should be multiplied to 42.022 and minus, once again, 0.1 times CP0, which is 1.0045 times, this time is temperature at 0.3, which is the outgoing temperature, and this value is 30 degrees C. It would be 303 kelvins plus W3, which we calculated it, and it is 0.02503 times the enthalpy, the vapor enthalpy at 30 degrees C, which we know it from the table to be 2555, 2555.6, and plus Q dot, and the outcome for Q dot would be 8.0549 kilowatts. And therefore, as it is, we have calculated this problem very simple and straightforward. But there are peculiarities at point 2, which we have to consider in the next video. Thanks for watching, and cheers.